Given a matrix A, let's now discuss how to go about figuring out the eigenvalues for that particular matrix. As a reminder, what we're really studying here is the equation AX equals lambda x. X is a vector called the eigenvector, and lambda is a scalar called the eigenvalue. Whenever you can write down an equation like this, where the effect of A on some vector is to scale it by a certain amount, then you're dealing with an eigenvector and an eigenvalue. So how do we figure out if a matrix has these things? Let's start by looking at a particular example. The matrix is minus 1, 0, 0, 1, and we like to think of this as a linear transformation of R2, meaning if you take a vector in R2 and you apply this matrix, you're going to get another vector in R2, and that vector is A times V. So what exactly is this linear transformation? What does it do? This one does reflection in the y-axis. You can see that by just taking a coordinate xy, and then if you apply the matrix to it, it sends xy to minus xy. And pictorially, think of a vector being reflected across the y-axis over here. And it doesn't matter whether you pick the vector that I drew here in the picture or any other vector, it's going to have the same effect of reflecting it across the y-axis. So let's think now about what is actually fixed. What doesn't change when you apply this linear transformation? And by fixed, what I really mean is that a vector is sent to a parallel version of itself. Maybe it's stretched out or maybe it's stretched back, but it has the same direction. Well, when the linear transformation is reflection in the y-axis, there's really only two types of vectors that are going to go to some version of themselves. There's vectors that lie along the x-axis. That's what I have pictured in red. This vector is going to get sent to itself, but pointed in the opposite direction. In other words, v will get sent to minus v by the transformation. The other type of vector that's going to get sent to itself is a vector that is parallel to the y-axis itself. Because you're reflecting in the y-axis, it's not going to go anywhere. Given that this is the situation, I'm going to make an educated guess about what the eigenvalues and eigenvectors should be. I'm going to guess that one of those eigenvectors is 1, 0 and the other is 0, 1. Because those are your basic unit basis vectors that actually lie on the x-axis and the y-axis, pictured in red and blue here. And my two eigenvalues, I think that they're going to be lambda equals 1 and lambda equals minus 1. 1 for the vector that stays put and minus 1 for the vector that gets flipped in the opposite direction. What we're going to do next is actually validate this guess with a procedure that you can follow. So to actually solve for lambda 1 and lambda 2, rather than making a guess, let's observe something. If lambda is an eigenvalue, then there's some eigenvector x, and ax is equal to lambda x. We can rewrite this equation to just say that ax minus lambda x is equal to the 0 vector. And then we're going to do a little trick. We're going to insert the identity matrix in between lambda and x. It doesn't do anything because the identity matrix times x still gives you x, so you can put that in at no cost. But now what we're going to do is pull the x out of the equation. And in parentheses, what we have is a minus lambda times the identity matrix. And all of this together is a matrix. So what we have now is a matrix times a vector, giving us the 0 vector. And that was a good trick because rewriting it this way means that what we're staring at is a homogeneous system of equations. Matrix times vector equals 0 is the matrix way to package up a homogeneous system. And remember, homogeneous just means set equal to 0. And at this point, we have a lot of linear algebra that we've built up to study homogeneous systems of equations. What we can actually say is that this system has a non-zero solution x. That's the eigenvector that we're looking for. If and only if the matrix A minus lambda I, that's the matrix appearing in this equation, has determinant 0. And the point here is that if the matrix, the square matrix A minus lambda I, is determinant 0, then it's not invertible. And that means it's going to have some non-trivial null space. If we give it the name B, say, if bx is equal to 0, then the vector x is in the null space of B. It has some null space happening. And this is great because it gives us a strategy for how to solve for the eigenvalues lambda. To find the eigenvalues, we've reduced it to solving for values lambda that solve the equation determinant of A minus lambda I equals 0. Let's see it happen in the example. The particular matrix we were looking at that did the linear transformation was minus 1, 0, 0, 1. So in this case, we're going to be looking now at not A, but A minus lambda I. So that's this particular matrix, and then we subtract the scalar lambda times the identity matrix. So we multiply the lambda through the identity matrix, and adding these two together, then we're left with a 2 by 2 matrix. So when we calculate the determinant of A minus lambda I, we're calculating the determinant of this matrix that has little lambdas as its entries. Even though those entries are symbolic, we can still use our 2 by 2 determinant formula, AD minus BC, And that gives us an expression that has lambdas in it. It's a polynomial in lambda. And I'm going to take this polynomial, I'm going to simplify it, and then I'm going to factor it so that I can find the roots. In this case, that's plus and minus 1. And we're looking for the roots because we're trying to figure out when the determinant is equal to 0. And if lambda is 1 or minus 1, that's going to make this entire determinant 0. The determinant being 0 corresponded to the existence of some eigenvector tied to some eigenvalue. So this means that the roots of this polynomial equation, lambda equals plus 1 and minus 1 in this case, are the two eigenvalues for that matrix. By the way, this polynomial that you produce when you calculate determinant of a minus lambda I has a special name. It's called the characteristic polynomial. Eigenvalues are great, but that's just part of what we're after. Next, let's find the eigenvectors that correspond with those eigenvalues. In this problem, we have two eigenvalues, lambda 1 and lambda 2. These are going to be plus 1 and minus 1. And for each one of them, we're going to look now at the matrix a minus lambda I. In other words, you're just going to be plugging in the lambdas into this matrix a minus lambda I that you produced above. In the first case with plus 1, this is going to end up giving us minus 2, 0, 0, 0. And now what we're essentially going to do is to write down a basis for the null space of this matrix. We're going to do this calculation in a similar way that we did earlier in the semester. I'm going to put my matrix 2, 0, 0, 0 in reduced row echelon form. In this case, it's just going to boil down to 1, 0, 0, 0, and then I write down my single basis vector for this null space. That works out to be 0, 1. You can get this vector by either analyzing the linear dependencies of the matrix, or you can convert your reduced row echelon form matrix into a system of equations and find it that way. Either way works. And what we see here is that the null space of this particular matrix, minus 2, 0, 0, 0, is one-dimensional. The basis vector is the eigenvector v1 for lambda 1. Now we repeat the same process for the second eigenvalue, lambda 2. Lambda 2 is minus 1, and so we again plug it into this matrix. That's what this is. And it gives us 0, 0, 0, 2. I'm again going to write down a basis for the null space of this matrix. So I row reduce it, and I find out that that basis vector is 1, 0. And again, I have that this one basis vector that I produced is the eigenvector for lambda 2. Let's not forget the source of this example. It came from the linear transformation that took a vector and reflected it across the y-axis. And the initial guess that we made based on the behavior of this linear transformation is that there should be an eigenvector 0, 1 and an eigenvector 1, 0, and that the corresponding eigenvalues should be 1 and minus 1. And lo and behold, that's what we produced. We found explicitly with this calculation that we had an eigenvalue of 1 with a corresponding eigenvector of 0, 1. This indicates that that's the y-axis and that it's fixed under the transformation. We also found lambda 2 being equal to minus 1, and its corresponding eigenvector was 1, 0. So that says that the x-axis is also going to be fixed in the sense of going to a parallel vector, and in particular, this one is going to get sent to itself in the opposite direction. Let's now summarize what we saw in this example as a theorem. A is a square matrix. The eigenvalues are the scalars lambda that are the roots of the characteristic polynomial, determinant of lambda I minus a. This is effectively the way that you find the eigenvalues. You calculate the roots of the characteristic polynomial. The eigenvectors of the matrix that correspond with an eigenvalue lambda are the non-zero solutions to the null equation, lambda I minus a x equals 0. One thing that I'll mention is that it doesn't matter whether you take lambda I minus a or a minus lambda I. Sometimes I do it one way and sometimes I do it the other way. You're taking an equation set equal to 0 and multiplying through by minus 1, so it doesn't really change anything. Let's now run through another quick example of a 2x2 matrix to see how this all works. We're going to find the eigenvectors and eigenvalues of 2, 2, 5, minus 1. The first thing to do is to write out the characteristic polynomial. That means finding the matrix lambda I minus a, which if you take lambdas down the diagonal and zeros everywhere else, that's lambda I, and subtracting a gives you lambda minus 2 minus 5 lambda plus 1. Note the sign changes with the 2 and the 5, that comes from subtracting. And now we're going to calculate the determinant of this 2x2 matrix. Working out this determinant is going to produce a polynomial because there's lambdas as entries of this matrix. So we write out, using the 2x2 determinant formula, AD minus BC, this expression, expand it, regroup terms, and factor. Now it's easy to see that the roots of this polynomial are 4 and minus 3. And those roots are our two eigenvalues, 4 and minus 3. And for each of these eigenvalues, we're going to work out what the corresponding eigenvector is. Let's do it for lambda equals 4 first. So what we do here is we take again this matrix lambda I minus a. That's lambda minus 2, minus 5, lambda plus 1. And now we're going to plug in 4 where there's a lambda. Now I want to find a basis for the null space of this matrix, and it's still just a simple 2 by 2 matrix. So all I really have to do is 1 or 2 row operations to put it into reduced row echelon form. And then I write down a basis for the null space. Next, I'm going to repeat this calculation for the eigenvalue minus 3. So that means I'm going to take minus 3 and plug it into the matrix lambda minus 2, minus 5, lambda plus 1. That's how I get the entries of minus 5 and minus 2 going down the diagonal here. And again, I'm going to row reduce this matrix. When I have my row reduced matrix, it's easy for me to read off what the basis vector for the null space is. And again, I get this vector x2, which is minus 2/5, 1, that corresponds with my eigenvalue. Now, in this example, I'm getting one eigenvector for the basis of my null space, meaning it's a one-dimensional eigenspace, but that's a coincidence of it being a small example, only a 2 by 2 matrix. In a larger or more complicated example, you could definitely see more vectors in the basis for the null space. One question that might still be remaining about this example is really how I go about getting x1 and x2. These are basis vectors for a null space, and I'm using the same procedure that we used earlier in the semester when we calculated bases for the 4 fundamental subspaces of a matrix. But some time has passed, and so I want to go over how exactly I got x1 and x2. It might be helpful in this calculation to remember that I'm solving a null equation. I have a matrix times the vector x, and I want to know when this is equal to 0. And that matrix happens to be lambda I minus a here. So I'm going to be row reducing my matrix and then trying to write down basis vectors for the null space. Let's look at the first calculation. My matrix, once I have actual numbers in it, row reduces down to 1, minus 1, 0, 0. And you might find it helpful to think about this as representing a system of equations. If I write down that system of equations, it's going to be x minus y equals 0 and 0 equals 0. This is the null equation, so everything's set equal to 0. And so in particular, x is equal to y is free, and when I parameterize solutions, I should name y. So say y is equal to t, where t is any real number. And then my solutions to the system of equations would look like t. And treating t as a scalar, I can write it out front, so it's t times the vector 1, 1. And that's this vector right here, that's 1, 1. Another good way to get at this answer is to go directly from the matrix. So I could write down 1 minus 1, 0, 0, and simply observe that column 2 is equal to minus 1 times column 1. And I can rewrite this equation so I'm setting it equal to 0. And now 1 times column 1 plus 1 times column 2 is equal to the 0 vector. And it's those two coefficients, 1 and 1, that populate this vector, 1, 1, and that I see here, 1, 1. So those are two different ways of getting to this answer. Let's look at the second calculation as well. In this case, my matrix row reduces down to 5, 2, 0, 0. Again, I'm going to think about this as a system of equations. This tells me that 5x plus 2y is equal to 0, and 0 is equal to 0. And so now this tells me that x is equal to minus 2/5 y. And from here, I can name y, set y equal to t, and then I get out of this minus 2/5 for x, 1 for y, and that parameterizes the set of solutions, and this particular vector that shows up is the minus 2/5 and the 1 that I saw here.